Lewis structures. So I think what people need to do is to look at the different types of bonding environments that we commonly encounter. For example, hydrogen, always just a single bond. Carbon's going to have 4 total bonds. It could be 4 single bonds in a tetrahedral arrangement like this. We call this tetrahedral carbon. It could be 1 double and 2 singles. This would be a trigonal planar arrangement here. Or it could be a triple and a single. There are others, but the others you don't get to until organic chemistry. That is, ones with a formal charge. For nitrogen, it can be 3 single bonds and a lone pair. So it'd be like a trigonal pyramidal type arrangement like this. This is a tetrahedral electron geometry. Or it could be a double and a single, like this, in a trigonal planar type arrangement here. Or it could be a triple bond there. We also have nitrogen with a positive formal charge, which would be a tetrahedral arrangement around there, and nitrogen with negative formal charge, which would be a bent or angular arrangement like this, a bent at 109. So these are very common for these. When we go to oxygen, we see 4 different styles of oxygen. This one we call a bridging oxygen, and just bridges. 2 single bonds here, 2 lone pairs, tetrahedral or bent. This lone pair sticks out, this lone pair sticks in. This is called a terminal oxygen. It's just double bonded at the end. This is trigonal planar. So you have a trigonal planar arrangement here. This is an oxygen with a positive formal charge. Rather than forming 2 bonds, like the previous 2, it forms 3 bonds here. So we've got 3 single bonds and a lone pair. Like hydronium. This is oxygen with just 1 bond and 3 lone pairs. They have a negative formal charge here. Then we could have oxide as well, nitride, carbide. Fluorine only forms a single bond here, shown here. These are typical bonding environment for these. These will help you with the Lewis structure. There are some others that we need to pay attention to. Unlike nitrogen, phosphorus is more. Phosphorus, because it's in the 3rd shell, so it can expand its octet. And so phosphorus is going to be like nitrogen. You could have 3 single bonds in a trigonal pyramidal arrangement like this. Phosphorus and nitrogen are in the same family. You could have a double and a single like that. In a trigonal planar type arrangement. Trigonal planar. But it could also do this. Phosphorus could have a double and 3 singles with no formal charge. And that would be in a tetrahedral arrangement. That's because it could expand its octet. This is expanded octet. Nitrogen cannot expand its octet, but phosphorus can. Expanded octet. Another expanded octet for phosphorus is when we have 5 single bonds. 1, 2, 3, 4, 5. 5 single bonds. This one is Chem 1A. This is called trigonal bipyramidal. Chem 1A. The geometry. This is Chem 1A. 5 single bonds. Likewise, they could do the same thing as nitrogen. They could form 4 single bonds with a positive charge, like that, missing an electron. Or it could form a negative charge as well. 2 lone pairs. So it's similar to nitrogen, except it has these 2 extra ones here from the capability of handling out an expanded octet, whereas nitrogen won't. Sulfur is in the same family as oxygen, and so it's going to show all these plus 2 more. So I'm not going to draw the ones that are the same as oxygen. Same as oxygen, same as oxygen, is with 6 single bonds, like that. This is also a Chem 1A type structure. Chem 1A type structure, we call this an octahedral structure. Chem 1A. But sulfur can also form, the other most common one was with 2 double bonds and 2 single bonds, like in sulfuric acid or something like that. This one's going to be tetrahedral, so we can draw this one out. Tetrahedral in that sense. So both of these are expanded. So once we get to the 3rd shell and 4th shell, 5th shell, we can expand the octet and get different bonding environments shown there. Okay, are you there yet? No. Okay, I wanted to talk about the quiz, but I'll wait a minute for that. Not worth that much. Not going to deduct much. And so, did we finish the acid-base problem we were looking at yesterday? Sodium sulfide with sodium chloride. Did we finish that one?
No, we didn't.
No, we didn't. Let's do that one now. And okay, today what I want to do is I want to end early and just skip the break. Is that okay?
Sure.
Yeah.
All right. We're gonna end. I have an appointment I have to go to. So we're looking at this. I think sodium sulfide solid plus sodium chloride, AQ. And in this particular reaction, there's no metathesis. There's no double replacement. Even though there's AB plus CD, we're just going to get sodium chloride and sodium sulfide. So there's no change here. So we look for acid base. So if we look for acid base, then we're going to analyze this. And so what we'll do is step 1, inventory. Sodium ion, sulfide ion, chloride ion, and one more species. Is that one more species? Water. The last species here. All right, then we analyze. Sodium ions are what? Acid base or neutral?
Neutral.
Sulfide?
Yes.
Sulfide turns out to be a powerful base. Yeah, let's take a look. I'll show it to you. Sulfide turns out to be a strong base. You see it here? Stronger than hydroxide, even. It's the base. Chloride. Chloride's an exceptionally weak base. Chloride is such a weak base that most people don't even consider it a base. So it's close to neutral. So base, but let's put a little asterisk here. Neutral. Well, it's because it's just too weak. Water, acid, and base. It's amphoteric. None of these other species are amphoteric. And so in the next step, we pick the strongest acid. What's the strongest acid?
H2O.
H2O. And we pick the strongest base? Sulfide ion. And then we transfer. What we're going to do is we're going to transfer one hydrogen from the acid to the base. And I think we already did this. We got hydroxide and hydrogen sulfide ion. We're just transferring one H plus. And so this is our acid and base in the forward direction. If we were to reverse this, what's hydroxide? The acid or the base? The base, and then HS minus is the acid. And then we're going to compare the strengths here. HS minus versus hydroxide. Which one's stronger?
HS minus.
Which one's stronger? Well, you can't say HS minus is stronger than hydroxide. Why?
They're right next to each other.
Well, there's one other reason why. Yeah, we're looking at different charts here. This is the apples, and this is the oranges. And so the biggest oranges are down here. The biggest apples are up there. And so HS minus is an apple. We can't compare that to this. So we'll have to look hydroxide versus HS minus. So we got to find HS minus. So I got to scroll up. You see it? Here? Here's HS minus. Here. But you know what? We're not comparing HS minus versus hydroxide. What should we be comparing?
Bases to bases.
Bases to bases and acids to acids. And so if we're going to compare the bases, then we should look at sulfide versus hydroxide. So let's take a look at that. When we look at sulfide versus hydroxide, which one's stronger?
Sulfide.
Sulfide. And so we're going from stronger base to weaker base. That's driving force right there. The acids have to follow because of the conjugate relationship. It turns out it's got to go strong, strong, weak, weak, or weak, weak, strong, strong. You can't go both. And so when we look at the acids here, let's compare the two acids. HS minus is one acid, and water is the other acid. Which one's a stronger acid, water or HS minus? Water. So this is stronger, weaker. Therefore, we have reaction. We have an acid-base reaction occurring here. Okay, are there any questions on that? Okay, this is how you do acid-base reactions. We just use the chart to figure it out. Okay, next what we're going to do is we're going to look at pH. When we look at pH, we're looking at an acid-base reaction occur. Let's just look at water, pure water, for right now. Okay, did I get all the quizzes back? Yeah. All right. Before I talk about pH, let me talk about this quiz. This quiz. First, you have to have the balanced chemical equation. CH4 plus 2O2 yields CO2 plus 2 H2O liquids. And then we make an assumption that the temperature and the pressure don't change. And so the mole ratio, if the temperature and pressure don't change, then the mole ratio is the same as the volume ratio according to Avogadro's law. And so going back to this quiz, I would have done it this way. 53 liters of methane. So I have 53 liters of methane, CH4, and then the volume ratio is 1 liter of CO2 for every 1 liter of methane. And so the yield of CO2 is 53 liters of CO2. That's from part A. Then part B, we're looking at the air. The air is 512 liters of air. But air is not pure oxygen. There's 21 liters of oxygen for every 100 liters of air, according to Avogadro. And then the volume ratio, 2 liters of O2 for every 1 liter of CO2. So 1 liter of CO2 on top, 2 liters of O2 on the bottom. And so 512 times 21 divided by 100 divided by 2. So let's see what that comes out to. So 512 times 21 divided by 2. So let's see what that does that come out to. What do you get?
I got 53.76.
Okay, 512 times 21 divided by 2. Divided by 100. 53 53.76 liters of CO2, which means what? Which one's the limiting reagent? Methane. We cannot get that extra 0.76. We're going to get 53 liters because we don't have enough methane to react with all the air. And so in this case, methane is the limiting reagent. And so, you know, the more tools you have, you know, the more speed you'll have. And at UCLA, the exams are, and UCSB too, the exams are timed. You don't have much time, so you have to be quick. And so, you know, if somebody can do this problem in a couple of minutes, they're going to have a huge advantage over somebody who might take, you know, longer. You want to think about that. And then the curve is going to be distributed, you know, perfectly. A lot of classes are curved. But that comes with practice, so we're just doing this. Practice comes through doing the homework. All right, let's go back to this here. Next slide. Is that a favorable reaction at the top? Okay, let's take a look at that acid-base reaction. These are all Bronsted acid-base reactions. So I'm going to have H2O liquid plus H2O liquid. We're going to have two water molecules react. Now, water is amphoteric, so one water I'm going to call the other water I'm going to call the base. And so I'm going to label this one, the first one the base and the second one the acid. It doesn't matter, you can flip it if you want. But what do bases do? And what do acids do? Bases take the hydrogen. And so this base is going to form this acid. This base forms this acid. And acids lose the hydrogen. We're going to be left with hydroxide. So these are the pairs here. This is the base acid base pair. Okay, if we reverse this reaction, we see the same thing here. Here, the hydronium loses, the hydroxide gains. All right, now let's do the driving force for this. Which one's a stronger? Do we need the table for this? Which one's a stronger acid? Hydronium or water? Which one is a stronger acid? Maybe we'll take a look at the table. Okay, here's hydronium here. We'll scroll down until we get to water. Here's water down here. Which one's stronger?
Hydronium.
Hydronium's stronger. Weaker. Which base is stronger? Hydroxide or water? Here's hydroxide. Here's water.
Hydroxide.
Hydroxide's stronger. Weaker. And so what we say is there's no driving force, right? This is uphill reaction. It's quite steep because, you know, water is not strong at all. This is quite a steep hill to get up, right? And so most of the water molecules aren't going to get up there. But, you know, not all water molecules have the same energy. There's a tiny fraction of water molecules that are quite energetic. And so let's say I put a billion, if I put a billion water molecules in this beaker, are all billion water molecules in that beaker, do they all have the same energy? No. There's going to be a small fraction that have much higher energy. In fact, in that billion water molecules, there's going to be about 4 water molecules that have enough energy that when they collide, they can climb this hill right here. This is a very unfavorable reaction, but there are about 4 that can actually make it up here to form hydronium and hydroxide. And so a tiny, tiny bit of reaction actually occurs. Extremely small amount of reaction occurs. You know, normally we don't think of, when we think about water, we think of water molecules. We don't really think about hydronium and hydroxide. Well, a tiny, tiny fraction of this occurs. here. So this water reacts with this water to form hydronium and hydroxide. Well, how much reaction occurs? Well, we can measure how much reaction occurs. And the amount of reaction that occurs is this. In this water, this is just pure water, we can measure how much by determining the concentration. It turns out that 1 times 10, actually let's get the right number of sequence. 1.0 times 10 to the minus 7 molar hydronium forms, and 1.0 times 10 to the minus 7 molar hydroxide forms. This is going to be at 25 degrees C. So that's about 4 parts out of a billion. So a tiny bit of reaction does occur. Tiny bit of reaction to form this amount of product here. So for every liter of water, I'll have 10 to the minus 7 moles of hydronium and hydroxide per liter of water. Okay, now we're going to talk about the pH. P, this is for power function. Power function. Power function, this is just the negative of the power. Let me give you some pHs here. Negative of the power, it's a power function of the H plus concentration. Negative power of the H plus concentration. And so we're going to go through this here. Let's say I have 1 molar H plus. Then the power is this. It's 10 to the 0th power molar H plus. And then the pH is equal to 0. Let's go to 0.1 molar H plus. 0.1 molar H plus gives me 10 to the minus 1 molar H plus, and the pH is 1. 0.01 gives me 10 to the minus 2, which means the pH is 2. 0.001 is 10 to the minus 3, which gives me a pH of 3. 0.0001 is 10 to the minus 4, pH is 4. 0.00001, 10 to the minus 5, pH is 5. 0.00001 is 10 to the minus 6, pH is 6. 0.00001 is 10 to the minus 7. 10 to the minus 7 molar H plus, or H3O plus. H plus and H3O plus are thinking the same. That's pH 7. And so pure water has a concentration of hydronium of 10 to the minus 7 molar. 10 to the minus 7 molar is pH 7. Now, we have this coefficient here, 1.00, and so it's actually going to be 7.00, the correct number of sig figs. In power functions, the sig figs are after the decimal, and so we count this as 2 sig figs. In the coefficient over here, we count these as 2 sig figs over here, so we end up with 2 sig figs there, etc. You know, we can keep going here. And so, really, what we have is 0.0000001 molar. A tiny bit of reaction occurs to make water pH 7. So pure water is pH 7. This is called the water equilibrium. So pure water at 25 degrees C has a pH of 7 here. But what happens if you dissolve stuff in here? What happens if you put other like acids or bases in here? It's going to change the pH. So what we do is we have something called KW. KW, this is for both pure water and solutions. KW is a constant at 25 degrees C and equals 1.0 times 10 to the minus 14. It's KW. What KW equals is it's going to equal the hydronium ion concentration times the hydroxide ion concentration. These square brackets represent concentration, the molar concentration. And so for pure water, this is what we get. For pure water at 25 degrees C, KW is equal to the hydronium ion concentration times the hydroxide ion concentration. Hydronium ion concentration is 1.0 times 10 to the minus 7. Hydroxide is 1.0 times 10 to the minus 7. KW doesn't have units, and so I'm going to drop the units for this. And we end up with 1.0 times 10 to the minus 14. The unit should be molar squared, but it isn't. So it's KW. What happens is this. For solutions, we add acids or bases, it's going to change the pH. So for solutions, we add acids or bases, and this is going to change the pH. And so what's going to happen is it's going to alter the hydronium hydroxide. All solutions contain hydronium hydroxide. So when the hydronium concentration equals the hydroxide ion concentration, we call that neutral. If we have more hydronium, let's say we dump in extra hydronium in there, so if the hydronium concentration is greater than the hydroxide concentration, we call it acidic. If the hydronium ion concentration is less than the hydroxide ion concentration, then we call the solution basic. Now, KW has to hold for all solutions. And so there's going to be some interesting relationships for this. So what that means is that if I increase the hydronium, the hydroxide must come down. Or if I increase the hydroxide, the hydronium must come down. It's going to be a seesaw because it's got to maintain that same concentration. So this is what this is showing here. For neutral solutions, the hydronium is equal to the hydroxide concentration. If I dump in some acid in there, this is what's going to happen. The hydronium is going to go up. If the hydronium goes up, then the hydroxide must go down, because this times this has to equal 10 to the minus 14. And so these two have to add up to 14. So 7 and 7 add up to 14. 6 and 8 add up to 14. If I make it even more concentrated, 10 to the minus 5, then this has got to go to 9. Yeah. You see that seesaw relationship there? So as the hydronium ion concentration increases, the hydroxide ion concentration has got to decrease. It gets smaller. Likewise, let's say I add some base to this. Acids would be like black coffee, tomatoes, wine, vinegar, lemon juice, stomach acid. Adding acids. Likewise, let's say I'm going to add base to this, like bicarbonate, borax, milk of magnesia, ammonia. then the hydroxide is going up, and the hydronium must be going down. So in all these, the hydroxide is greater than the hydronium. In all these, the hydronium is greater than the hydroxide. So acidic solutions and basic solutions. We have strongly acidic solutions would have low pH here. Neutral would be 7. Weakly acidic would be like 5, 6. Milk is weakly acidic. Strongly basic, now the hydronium goes way down. Strongly basic solutions are going to have pHs above 7. You know, above 7. And strongly basic would be like 13, 14 plus. And these would be moderate, and this would be weakly basic. All right, so those are the pHs and some solutions here. Now, there are going to be some other relationships that we're going to see. So what we're going to do is we're going to do pH, pOH, pKW, KW. And we're going to look at relating these things to each other. So the first thing is the pOH. Let's go with pH. First thing is the pH. pH is the power of the hydrogen ion concentration, or the negative log of the H plus concentration, or H3O plus concentration. That's how we can calculate the pH. The pOH is the same thing except for the hydroxide concentration. The pOH is equal to the negative log of the hydroxide ion concentration. And so it's just the power, the negative power. So if the pH is 14, what is my pOH? This is 1 is 10 to the 0, so my pOH is 0. If the pH is 13, what is my pOH? This is my pH. My pOH is 1. If my pH is 12, what is my pOH? 2. If my pH is 9, my pOH is 5. And so that's what we have here. The way we're going to relate these is different ways, but here we can go from the P. Oh, actually, I should do it this way. The H plus concentration is just going to equal this. Actually, I'm not going to do too many equations here. We're going to be able to tie all these together. So in order to tie these, we use Kw. Kw is equal to the hydronium ion concentration of the H plus concentration times the hydroxide ion concentration, which equals 1.0 times 10 to the minus 14. A pH and pOH can be related by something called pKw. pKw is equal to 14.00, which is equal to the pH plus the pOH. And so these are the calculations that we will encounter here. So let's take a look at these calculations here. Determine the hydroxide ion concentration in the solution in which the H plus is 10 to the minus 5. Well, if the H plus is 10 to the minus 5, then the hydroxide's got to be 10 to the minus 9. Yeah, the hydroxide's got to be 10 to the minus 9 because 5 and 9 make 14. So let's take a look. Yeah, 10 to the minus 9. Is the solution acidic or basic? It's acidic. 10 to the minus 5 is greater than 10 to the minus 9, so it's acidic. We could use the equation to do it too. For example, we could use the Kw equation. Take Kw 10 minus 14 divided by the H plus 10 to the minus 5 gives us 10 minus 9. We could do it that way too, algebraically. Well, let me throw in a couple more things. The H plus is 10 to the minus P pH molar. And the OH minus is 10 to the minus POH molar. If we want to calculate it that way. And so this is the loop here, the pH loop. Probably better than what I drew there. Just use it. So what are the pH, POH, hydroxide, and H plus of the 0.01 molar sodium hydroxide solution? Okay, so do it this way. We're going to have 0.01, so 0.01 molar sodium hydroxide means that we have 0.01 molar hydroxide, sodium hydroxide that splits up into sodium hydroxide on it, which means that this is 1 times 10 to the minus, what? 1 times 10 to the minus 2. 10 to the minus 2 molar hydroxide. So what is the POH, the power of the hydroxide, the negative power of the hydroxide? Well, the power is going to be 2, so the POH is 2. And it's going to be 0.0 because of this. We have 1 sig fig. If the POH is 0, then what is the pH? The POH and the pH have to add up to 14, so the pH must be 12.0. And that means if the pH is 12.0, what is my H plus concentration? Well, the H plus concentration is 10 to the minus 12 molar. And how many sig figs? I'm allowed 1 sig fig, so there's 1 sig fig. And so what I'm going to do is I'm going to write it like this. 1 times 10 to the minus 12 molar would be it. Okay. But there are different ways of measuring the pH. This is called indicator paper. So we can just check the paper's color to determine the pH from acidic to basic. We can use a pH meter. This pH meter has a probe that's sensitive to the pH. This pH is 4.33. pH is 4.33. Is that acidic or basic? That's acidic. pH is less than 7 or acidic. pH is greater than 7 or basic. Okay, when we have this, when we have, so far the coefficient's always been 1. But we might have non-integer coefficients, or it could be 2, that could be an integer, but, and so here we have to use a calculator to do it, in this case. So let's do it here. So we can't just take the power because it's the hydrogen ion concentration, H plus, in this example, is equal to 2.7 times 10 to the minus 6 molar. We can't just take the power because the coefficient is not 1. And so if we want the pH, we have to use the calculator. Negative log of 2.7 times 10 to the minus 6. And so we just punch it on our calculator. .7 times 10 minus 6. Then take the log of that. Log base 10, 6.15. So it has a pH of 6.15. Now how many sig figs? I'm allowed 2 sig figs. So these are 2 sig figs. This is 2 sig figs. 6.15, I'm going to carry 1 extra, 4. That's the pH. if that's the pH, what is my pOH? Well, 14, my pOH is gonna be 7.845. And what is my hydroxide ion concentration? There are two ways of getting the hydroxide ion concentration. I'm gonna get it the Kw divided by the hydrogen weight this time. And so Kw is 1.0 times 10 to the minus 14, that's 2 sig figs, divided by the hydrogen ion concentration of 2.7 times 10 to the minus 6 gives me 1 times 10 to the negative 14. Times, or divided by 2.7 times 10 to the negative 6. And I get 3.70 times 10 to the minus 369. If I didn't screw that up, let's see, 369.
I got a different number.
You got a different, what did you get?
I got 5.568. When you did the log of pH.
Oh, shoot. All right. That would really screw things up if I messed that one up. Let me, did other people get that?
Yeah.
What did you get?
5.56 subscript 9.
5.569. Yeah? Well,
It's because I think what happened was you did it to the positive 6.
oh. Yeah, I don't have my regular calculator. Let me see. Let me just do it one more time. You're right. But don't round this. It should be left at 5.568. But we don't round this. Just leave it as is. Okay, plus 14. You're right. I screwed that one up. This gives me 8.431. And then this one should be okay. Is it? Because I calculated it a different way. Yeah, it is. 3.7 times 10 to the minus 9. And so you're right. 5.57, 2 sig figs. 8.43, 2 sig figs. 3.7 times 10 to the minus 9, 2 sig figs. So for power functions, the sig figs are after the decimal. We don't count this as a sig fig. We count that as a placeholder. The sig figs are after. It's kind of weird, but that's what we do for power functions. The same thing, pKw is a power function. It's a negative log. Power function is always the same. It's a negative log of the item. Okay. Well, anyway, I'm going to cut short here. So I'll see you guys after the break, but you want to start doing some review, for the final. We'll start reviewing a little bit as we go along.